Welcome to this new video of Module 2, IPv4 Address Exhaustion, Coexistence, and Transition. In this module, we'll be talking about the dual stack strategy. We'll discuss the following topics: native IPv6, dual stack, and IPv6 only. Native IPv6. We've already seen that the recommended option for transitioning to IPv6 is native IPv6, with no packet encapsulation or translation. This will allow native IPv6 packets to traverse the network from source to destination using the IPv6 header for routing and other IP layer services. The main advantage of this strategy is that the schema, configuration, routing, and monitoring are future-proof, and no additional changes or improvements will be required for native IPv6 traffic to work. One might call this a one-step implementation, as opposed to the use of tunneling or translation-based transition mechanisms, which are temporary in nature and will require additional changes when these mechanisms need to be eliminated. On the other hand, this approach requires that all the elements involved in packet routing across the network support IPv6, which is not always the case. There are two options for deploying native IPv6: dual stack, where IPv4 and IPv6 are used in parallel, or IPv6 only, where the network only uses IPv6. Dual stack. The dual stack option consists of simultaneously enabling IPv4 and IPv6 on network devices so that IPv4 and native IPv6 packets can travel through the same network stack, interface, and wires. The advantage of this approach is that it does not affect IPv4 and allows IPv6 to be introduced gradually wherever possible. Typically, where both protocols are available, the default configuration places preference on IPv6. Over time, there has been a slight change in the default operating system preference for each protocol. Initially, preference was given to any IPv6 addressees, regardless whether it was native or used transition mechanisms. It then became evident that this could create problems if the transition mechanism provided a poor IPv6 service. So the current recommendation is to give preference to native IPv6, then IPv4, and finally IPv6 via transition mechanisms. The implications of the coexistence of IPv4 and IPv6 vary depending on whether we consider the data plane or the control or management plane. In the data plane, the traffic that moves to IPv6 ceases to exist in IPv4. In other words, no IPv6 traffic is added to the existing IPv4 traffic. For example, if a YouTube video is played over IPv6, it is no longer played over IPv4. This means that the introduction of IPv6 does not translate into the need to increase the bandwidth requirements of our infrastructure. However, the resources of the management or control plane do need to be increased, as the network will include a greater degree of complexity: 2 address spaces, 2 routing protocols, one for IPv4 and one for IPv6, dual configuration, double security configurations, one for each protocol. And all of this involves a cost in terms of both manpower hours and training. As the image shows, a service available on a dual stack server, for instance service.example.com, can be accessed from any type of host, IPv4 only, IPv6 only, or dual stack, using either version of the protocol. Both the IPv4 and IPv6 addresses will be published in the DNS, and the customer will decide which address to use. As we've seen, in most cases, default preference is given to IPv6. Here we can see an example of an Etho interface configuration in Linux. IPv4 and IPv6 are configured on the same interface such that IPv4 and IPv6 addresses are available at the same time, and it accepts traffic through both protocols. It then became evident that the static default preference for IPv6 could cause issues. Let's see an example where a customer tries to access a web application through DualStack. The DNS resolves the name www.example.com to an IPv4 and an IPv6 address. If, by default, it attempts to use IPv6 but connectivity is too slow or broken, it will perform a number of retries before switching to IPv4, which, if successful, will provide access to the website. The resulting user experience will be very poor, as each page that a user attempts to load will experience high latency, and the user will ultimately stop attempting to access the page. One solution to this problem is the so-called happy eyeballs mechanism. Let's see how this mechanism works using the same example as before. After resolving the website's DNS to both its IPv4 and IPv6 addresses, parallel attempts are made to connect via IPv4 and IPv6. After waiting for a bit, if IPv6 doesn't connect but IPv4 does, the decision will be made to access the website via IPv4. The user will notice practically no difference, as what really matters is the web page, not the protocol used to access it. To avoid executing this discovery procedure too often, this information about the domain is stored for some time, which also avoids sending unnecessary traffic through the network. This solution, flexibility in terms of the priority given to the network protocol to be used, is the default option implemented by Google Chrome and can be activated in Firefox. Another approach is to offer this service in the operating system itself, as is the case of Mac OS or Windows 8. IPv6 only. Finally, implementing native IPv6 without IPv4 is also an option. There are several possible reasons for choosing this option: a lack of sufficient IPv4 addresses, to simplify network management, for use with new IPv6 only services such as wireless sensor networks based on the 6LoWPAN standard, which is only defined for IPv6, to set up an IPv6 only server farm, which are then published in DualStack using load balancers, or to create an implementation that is valid forever. This option has a downside. How does one allow nodes on the IPv6 only network to access IPv4 only content? For these cases, we'll see that currently two options exist. First is the DS Lite tunneling, IPv4 encapsulated in IPv6, which allows you to offer IPv4 to end users. The second is the use of transition mechanisms known as NAT64/DNS64 or 464XLAT that have certain limitations and which are not compatible with certain applications. As more content becomes accessible over IPv6, this problem will tend to decrease. Thank you for your attention. We have just watched a video on DualStack. In the next video, we'll discuss tunneling.